Hello all, this is Ritika here. So I'll be explaining you about the boundary layer development and it is a part of fluid theory. Okay, so here when an object moves through a fluid, resistance encounters it, okay? As we all know. And this resistance is known as drag. Now this drag is of two types, that is skin friction drag and form drag. Now, what is form drag? Form drag arises when the pressure difference around the object influenced by how fluid flows and pushes against its shape. Whereas skin friction drag, it results from the frictional forces generated by fluid sliding along the surface of the object. And this together term is referred as a drag that a body experiences while traveling along the fluid. Then we'll study about the shear force and pressure force. What is shear force? It is also known as viscous drag, frictional drag, or skin friction, and arises in the fluid layer sliding past the solid surface, creating a shear effect. Now, this occurs flow expansion and related to the projected area facing the flow. Depends upon the surface area and length exposed to the flow. Now, pressure force, often referred as pressure drag or form drag, it results from the pressure exerted on the body and depends on the area of the object perpendicular to the flow. Okay, let's move ahead. Then, description of boundary layer. Okay, let's understand what is boundary layer. There is a wall shear stress here. Okay, the frictional force per unit area exerted by the fluid on the boundary surface. Okay, on the boundary surface, right next to the boundary. The fluid starts at zero and gradually climbs until it matches the speed of the main flow. And this thin region is called as boundary layer. Okay. Now within this layer, the velocity changes sharply. Okay, as we can see, creating significant velocity gradient that results in measurable shear stress. Okay, so here's that it will represent as tau is equals to nu du by dy. Okay, the boundary layer thickness is typically defined as a distance from surface to the point where the fluid velocity reaches 99%. Okay, that was boundary layer basic. Now, we'll study about the description of boundary layer consists of two layers. Okay, close to the boundary, outside the boundary layer. What is close to the boundary? Large velocity gradient. Okay, now outside boundary layer, there is viscous forces are considered as negligible. Okay, flow may be treated as non-viscous or invisible. Now, the shear stress that acts on a plate surface sets up a shear force. Okay, this opposes the fluid motion, in the direction fluid flow, and fluid close to the wall is deaccelerated. Okay, then development of boundary layer. Evaluation of boundary layer, as you can see, within a laminar boundary layer, fluid particle glide smoothly along defined streamlines. Okay, this thickening occurs because viscous forces increasingly sap the fluid kinetic energy, causing large clusters of particles to deaccelerate. This happens as the distance from the leading edge, that is here denoted as x, okay, leading edge, grows, the thickness of the boundary layer expands. Okay, small disturbance within the boundary layer amplify over time. Okay, next, this instability that shifts from laminar to turbulent flow, making oneself transition phase. Let's see, development of boundary layer continues as after going through this transition zone of finite length, the flow becomes completely turbulent. and this is characterized as a three-dimensional random motion of fluctuation induced bulk motion parcel of fluid. Laminar layer profile is parabolic, turbulent boundary layer profile is logarithmic. Okay. Now, boundary layer depends on Reynolds number, as you all know and studied, and also on the surface roughness, how the groovy surface. Okay, roughness of surface adds the disturbance in the flow. Okay, now there is a given formula for laminar flow and turbulent flow, that is tau is equals to nu du by dy. Then for turbulent flow it's nu plus epsilon du by dy. Okay, where there is eddy viscosity and it's much often than more than mu. Okay, then boundary layer thickness for laminar and turbulent flow. Boundary layer thickness for laminar flow, it is given as this formula as shown, and the for this also Blasius approximate solution, and this is for exact solution. Okay, 5.0 into x by root r e x, and here it is given as for turbulent flow for 0.377 x by re 1 by 5. Now this boundary layer thickness also have parameters like velocity, kinematic viscosity of fluid, and many more. Okay, then flow patterns and regimes within laminar and turbulent boundary layer. Um, कैसे flow patterns, like how flow patterns show as we saw above in slides. It's very close to the plane surface. Okay, the flow remains laminar and linear velocity profile may be assumed. In this region, the velocity gradient is governed by fluid viscosity, as we all show above here. Like, okay, here and also here we see that. Okay, now we'll study about the flow patterns and regimes within laminar and turbulent boundary. In turbulent flow, the random motion of fluid particle. Okay, here the patterns of eddy set up in boundary which sweep small masses of the fluid up and down the layer, moving action perpendicular to the surface in the mean flow direction. Okay, here you can see in this graph given below. Okay, I hope that is clear now. If now the slowing moving fluid is lifted upper levels, slowing down the fluid stream, and by doing so effectively thickening the boundary layer, explaining the more rapid growth and turbulent boundary layer compared with the laminar one. Okay, in order to explain this process, the eddy viscosity should added the shear stress formulation. Now this formulation becomes as given tau is equals to mu plus epsilon du. This we studied and this was the explanation of this. Okay. Now the effect, what is the effect of pressure gradient on the boundary layer development? What is that effect we see? The presence of pressure gradient, that is the flow stream velocity changes across the surface. Okay, and this gradient is shown by dou p by dou x, or you can say dou u by dou x. Now for example, consider a curved surface. Okay, velocity variance is shown below. Okay, see if dou u by dou x is greater than 0, velocity is increasing. Dou p by dx less than 0, pressure decreasing. Okay, now then if dou u by dou x is less than 0, velocity is again decreasing, and dou p by dou x greater than 0, pressure increasing. adverse pressure gradient. Okay, next we move on to effect of pressure gradient on boundary layer development. What is the effect? Okay, uh, see, if the pressure decreases in downstream direction, then the boundary layer tends to reduce thickness, called the favorable pressure gradient. And if we talk that pressure increases in the downstream direction, then boundary layer thickens rapidly, and this case is reversed as adverse pressure gradient, as shown here. Okay, that was a simple, and here this effect, because of this effect, we study the boundary layer thickness, reduce how it reduces and how it thicks. So this was boundary layer development. Thank you all. Have a great and nice day. I hope this was a better slide to understand the boundary layer development.